All right. Well, thank you very much for joining in the class today. We are going to start by answering questions about the project, okay, and seeing how things are going with that. Haley asked a very good question. She asked, what exactly the space mission we are trying to figure out is supposed to be. Also, the term systems needed to complete the mission didn't quite make sense. Okay, so I was kind of expected that you would have those type of questions. All right, and so this is what I wrote back to her. And I think that is important for everyone to understand. This is not a regular school assignment. Okay, so as you can imagine, in a regular school assignment, you are expected to get the right answer. So you do an exercise and there is a right answer. That is certainly not the case here. Okay, so most things in actual projects are ill-defined projects. Okay, so they are projects that don't have a specific objective, and part of the project is actually to define what the problem is, figure out what the solution to the problems could be, and so on. And so that is the type of project that we are trying to engage in here. Okay, so uh, for example, you can select an unexplored asteroid, and most of them are unexplored, and decide to send your Firefly probe to that asteroid. Okay, and today we are going to look at some other missions that have done similar things. So, um, is and actually in our okay, Sabrina. So you are if you have. So let me put something clear about teams and so on. If you are having trouble contacting the members of your team or something, I need you to send me an email here through the inbox, all right, a message there, and being able to modify teams or whatnot. Also, if you are participating in the class, either online or on your own, and you haven't been assigned to a team and would like to be assigned to a team, just let me know. Okay, also send me a message here through Canvas and let me know I need to be assigned to a team. Okay, and so, yeah, so I think that now we are starting to get a team happy, all right? So already being enthused about that. For example, I see that Ginger McGovern, join us in class now. I don't remember if Ginger, if you have been assigned to a team or not yet, okay? But just let me know. It's hard for me to keep track of these things unless you send me a message. Okay. So, as I was explaining, so that is Cassidy. All right, yeah. Okay, Cassidy, I think that I did assign you, so that's good. So the thing is that we need to basically decide, you need to decide as a team on what is it that you are going to do. Okay. As far as systems, what systems may be necessary to complete the mission, you basically need to decide, so there are going to be systems for launching, okay, the probe, other systems for providing energy to the probe, so solar panels, usually that is what they have. How are you going to manage or change the probe's trajectory? Okay. How are you going to communicate with the probe? Are you going to have cameras? Okay. How are you going to determine, the orbit, speed, size, mass, composition of an asteroid, and so on? All those things are systems. They are particular parts of the project that you need to basically figure out. Okay. And here we are basically in the design mode. We need to study what has been done, what are the possibilities for doing things, and then we need to decide, okay, how am I going to do that? All right, what are the things that I could do for that? All right. So you may want to work together as teams and decide first the first part, and this is due next week, is to do the report defining the mission of what you are going to do. And as I was studying this, I encountered a couple of missions that have already been done. And so I wanted to kind of share with you some of these missions, all right, some of things that have already happened. One of these missions was called Deep Space One, all right? So Deep Space One was launched in October 24th, 1998. Okay, so that is probably around the time that you were born, okay? And the spacecraft was retired in December 18, 2001. All right, so this was about a three-year mission. And this mission tested 12 advanced high-risk technologies in space, okay? And it was an extremely successful mission. It encountered a comet, okay, took images of the comet and everything, and they actually hyperextended the mission. Yeah, so this started in 1998. Okay, so here you see in the screen, 1998 was when it was launched. So here in this website, all right, you have information about what were the things that Deep Space One did, the things that happened, all right. So this is a good website to study. So you were born back in the middle of Deep Space One's mission, okay. So
born in November of that.
Sorry?
I was born in November of 1998.
Excellent. So, just a month after it launched. Good deal. Okay. So these are very exciting things, really, if you think about it. There's another, okay, sorry, let me go here. There's another mission that is currently going on called Dawn. So this is another probe that has been sent to encounter two asteroids. Okay, so this is this is the Wikipedia article on Dawn. This is the Wikipedia article on Deep Space One. So you can study this, all right, see what they achieved. In Deep Space one of the things that it did was it used a new propulsion engine, okay? So once the probe was in space, it needed to accelerate, or sometimes probes need to change the trajectory and everything. And so this was a new engine that is an ion engine, okay? And this article and some of the other links explain how this engine works. But basically, the basic idea of this ion engine, as far as I understand, is the following. Let me see, how can I draw this? Let's see if I can go to a blank screen here. Let's. All right, let's choose just a white page. Okay. All right, and just so let's see with a pen. Okay, I'm not very good at drawing here with a pen, but this is basically the engine, the ion engine of this probe. So it would have an opening on the front, okay, and small particles in space. So there's not a whole lot of things really in space, but the particles would enter in here, okay, then they would be ionized, okay, which is basically electrically charged, all right, so they are changed into an ion. So for example, if you have hydrogen, all that you need to do is to kind of charge it electrically to draw the electron away from the hydrogen, and so then you have a positively charged atom of hydrogen, and then that electrified hydrogen would go through some electromagnets, okay, so you know how magnets work, okay, so it would go through some electromagnetic field, and because the ion is positively charged, if the electromagnet here is negatively charged, so you have an ion that is positively charged and a field that is negatively charged here, what would happen? What would happen to the ion? You can put it on the chat, or you can open your microphone and think about what would happen with the ion that is positively charged, and then you have here a negatively charged electromagnetic field.
Would it expand?
Not expand. So what happens with magnets when you have magnets of opposite polarity? Okay, Sabrina, the positive and negative charges attract. Jen says they would attract each other. Exactly right. So this ion would start moving toward here to the magnet. Okay, it would be attracted, and it would actually accelerate in speed. All right. After it starts going here, then here there would be another electromagnetic field, okay, it would actually change the polarity of the field as it goes here, and it would go and be positive, okay, it would change into a positive field. And so what happens when you have a positive ion and now a positive electromagnetic field? Exactly, they would repulse each other, and so the ion would actually be repulsed and it would be compressed through a nozzle and expelled out. Okay, and so what you have here is this is kind of how the ion engine works, that it would capture molecules here from the front, accelerate them, and then send them out. Okay, and that would generate a very small, very small, minute thrust, okay? But as you put more and more of that thrust, okay, of that propulsion out, and this is in empty space, so there's nothing to, to stop the probe would start little by little accelerating, okay? So that is what an ion engine is, how it works in the theory. The interesting thing is that because the ion engine uses electromagnetic fields, all that it needs is electrical energy. And so the solar panels, remember how most of these probes have solar panels and everything, they would be used to generate the electricity in order to provide the energy to get the electromagnetic fields. Does that make sense? Okay, so that is a really cool thing, because with these engines you basically can change the trajectory, can give propulsion to the to the system without having to use propellant, okay? And whenever, if you have to use propellant, it's something that you have to transport and is consumed, all right? Instead, in this case, you are producing the energy and the propulsion right there in space, okay? So that is what this probe tried for the first time. This was the first time with deep space that they tried this engine. And so I want you to study this engine, how it works and everything. And Dawn, the other spacecraft that is actually currently in orbit, is also using one of these engines. In fact, it broke a speed record of acceleration in space because of this engine. All right. So Dawn was launched on September 27th, 07. Okay, so that is what, about 7 years ago. And the mission of Dawn was to study the two most massive objects in the asteroid belt. It was the protoplanet Vesta and the dwarf planet Ceres. Okay, and this is the interesting thing. Dawn is currently en route to Ceres, and it will arrive, is expected to arrive on March 9th. Actually, the other website says that March 9th of this year. Okay, so in about 2 months, we are going to arrive at Ceres. Okay, so this is actually really, really cool. We are going to be watching things as Dawn approaches Ceres and what it does with that. So this is an image of Ceres, okay, and we are certainly going to get better images as this happens, okay. So this is really, really interesting, and I want you to study these websites and so on. So the mission of Ceres, okay, the mission of Dawn is to study these two planets, and this is the trajectory, okay, yeah, in a dramatic voice, okay, as Dawn approaches, ta-tong, yeah. So this is the trajectory of Dawn. So it went, okay, it started here on Earth, and it went out, all right. It probably stayed around Earth's orbit for a while, and then it started the outward propulsion, okay. So here you see when there's the light blue is whenever Dawn has the thrust engine on, the ion thrust engine, okay. And so you see that during different periods of time, they were using that, and it used that thrust ion engine in order to go from Earth to Mars, okay? And then it went through Mars, and it got a gravitational assist, meaning an acceleration of Mars. And then again, it engaged the thrust engine, and then it encountered the asteroid Vesta, okay? And it stayed there with Vesta for all this time, and then it started the thrust engine again in order to reach Ceres. Okay, so this is Ceres now, okay, the where it is now, and this is the time when it's going to arrive. So this is going to take these next 2 months, all right? Yeah, so all this is using Kepler's laws of motion, of planetary motion, and Newton's laws of motion. Do you remember those lessons on that? So that is why it's so important for you to understand these laws. So when you decide in your project what is it that you are going to do, one of the things that you'll probably need to decide is what is going to be the trajectory, okay, of your mission. How are you going to do it? All right, and of course that it all depends on where you decide to go. if you are going to go to some of the near Earth asteroids, most of them are here between the orbit of Earth and Mars. There are some asteroids that cross the orbit of Earth, all right? And then, of course, there's the asteroid belt that has most of the asteroids is beyond the orbit of Mars, okay? So now, the Firefly probe is a lot smaller than Dawn or Deep Space One, all right? But we can assume, or we can think of, okay, are we going to use that type of ion engine, a mini scale of that, or what is it that we are going to do to have the propulsion necessary for that engine? Okay, so this is another picture of where things are now. Okay, this is at this today. So the position of Dawn relative to the Earth, the Sun, the Moon, okay? And here there's an article on space.com that says that this spacecraft broke the speed boost record, all right? So you can read more about how it did that here, and it went past 9,600 miles per hour mark. Okay, so a really, really fast acceleration that deep space got through this ion thrust engine. Okay, so and the thing is that this engine doesn't generate a lot of thrust, but it's just a little bit at a time accumulated over the whole time that the engine is on. So that is kind of how it goes. Okay, so do you have any questions about this so far? Okay, let's see. I think I have a couple. They have some websites here. Okay, so this is the website from the Jet Propulsion Laboratory on Deep Space One. What were the things that Deep Space One did? Okay, this website is probably the more complete, and I have there links on the lesson for this website. And it actually, this probe was very successful in completing all the objectives of the mission. Okay, so here we have in the Wikipedia article more explanations of that. Let me see now. We're going to go to this other part. Okay, so let's go at some things that I found very interesting. This website, and I also have a link of this in your lesson, it talks about how satellites work, okay? And these are for the low orbit satellites, the satellites that are in orbit around the Earth. And this article talks, and there are several pages on the article, but it's very, very interesting in talking and describing what is a satellite, how, the different types of satellites that we have, okay, how do they stay in orbit, what is the orbit that they need to reach, and so on. So very, very interesting and complete article on that. This YouTube video that also is linked in your lesson talks about how satellites work, okay? Especially these are the satellites that are geostationary, okay? So they are the ones that are positioned above the Earth, and they always stay around the same place. So if we go here, okay, so here I have a view of, again, the current conditions, all right? So this is Ceres, the asteroid in the asteroid belt, and currently how it is in position relative to the Earth, Mars, the Sun, okay? and the probe Dawn that is going to be approaching from here and going there. But if we go to the Earth, okay, you see that there are lots of satellites that are orbiting the Earth, and many of these satellites, all the ones that are used for telecommunications, are what is called geostationary, meaning that they stay on the same place relative to the Earth all the time, okay? So, for example, CSAT, all right, so let's see if this is a communication satellite, okay? Was the first Earth-orbiting satellite designed for remote sensing of the Earth oceans. Okay, so this is not necessarily a communication satellite, but you can find more about the different types of satellites and so on. Okay, let's see. How did I get back to the other view? Okay. No. I think that there may be a link here on this side. Okay. Ah, how do I get out of this view? Ah. Okay. All right. Well, so the geostationary satellites stay actually on the same place. Okay. And those are the ones that are used for communications, like TV stations and so on, GPS units. You also use those satellites. And this video explains really well how those satellites are kept in position. Okay. Here I have another website that is also linked to the lesson, to today's lesson, that talks about how do we communicate between these satellites, these probes that are in outer space and Earth. Okay, and what we have set up is basically NASA has what is called the Deep Space Network, and this is a network of 3 stations that are basically 120 degrees apart on the Earth, and there's one of these stations in close to Spain, in space close to Madrid. This is that one. There's one in Canberra, Australia, okay, and then the other one is in California, okay, in the Mojave Desert. So it's a very dry place, all right. But what happened is that as the Earth rotates, at any one time, one of these Earth stations can point to some of these satellites or probes that are flying in deep space, okay. So that is actually how NASA can communicate and also receive communications for these stations that are way out. Okay, so for example, here it talks about Voyager 1 and Voyager 2. They were those were satellites that were sent actually in the 70s. So when I was really small, you know, and they went through flybys of Mars, and then they flew by Jupiter and Saturn and Neptune. And I think that Voyager 1 was the first object to actually go out of the solar system. It went beyond the orbit of Uranus, okay? So now it is still out there working. It's still traveling out in space, and through these antennas, people on Earth can still communicate and receive information from these satellites. Okay, so you see they are very, very large antennas. There's three types of antennas here in this, and this this website explains pretty well and very clearly how things work. But they have, the small antennas are 111 feet in diameter. All right, so those are for the satellites that are close by, just the regular low orbit satellites. You also have, these are the 85-foot antenna is for the low orbit satellites. These ones are for a little bit farther. And then there's a 230-foot antenna. So this is the biggest antenna, okay, that is used to communicate with Voyager, all right, and those probes that are beyond Mars and so on. So in your project, you are going to need also to be able to communicate with your probe, okay? And so you will need to decide, what am I going to use in order to communicate with my probe? What systems is the probe going to have to receive information and to send information? And then how am I going to be able to listen and send information to the probe? You could decide as a team, okay, we are going to use NASA's Deep Space Network. It's already built, okay? By the way, NASA uses this also for, and they sell their time and availability for commercial or for other projects, okay? So that can also be used. But these are all things that I want you to study and learn about and think about, how am I going to do communications with my probe, okay? So any questions so far? Okay, I'm going to pause here for a second and see if there's any questions now. Okay, I think I need to click on that. All right, everything okay? So we talk about work as a team in deciding your mission. Okay, what are you going to do? What do you want to accomplish? And then we talk about some examples of other missions. We talk a little bit about propulsion in space, like using things like that ion engine. And also now we talk about the communication systems, okay? What are some possible communication systems that you could use to communicate back and forth, okay? Now, this is all aeronautics, okay? This is all basically how to fly, all right? Rockets and probes are basically like very, very high, fast airplanes, okay? They are not airplanes, they are space planes, but that is all the same type of idea. So now I have here a website that has an article written by Don Petit, okay? He is also a NASA astronaut. He wrote this article. Here we have a picture of him, and he was in the International Space Station. All right, here we have an article there in the Destiny Laboratory of the International Space Station. And this article talks about basically how do we get out of the Earth into orbit, okay? And he basically says that the loss of gravity and, you know, the mass of the Earth and everything are basically a tyranny, okay? It's nothing that you can change, okay? So you can ask questions both in the video chat or in here. If you have questions now in the lesson, you can do it here through the chat, okay? So let's see, what is he holding? I don't know the world is he holding. I don't know what. That is a camera here. So here he is holding one of the cameras in the International Space Station. Okay. So, but in this article, basically, Petit explains that there is an equation, and we are going to talk more about the equation. The equation is here in this other link, and I have it also that in the lesson. And this is the equation. This is called the Tsesian-Lovinsky equation, rocket equation. I have no idea how this last name is pronounced, but he was, see, what it would be, Slowkovsky's rocket equation. Wow, that's a mouthful. This guy was the so that guy was the, yeah, try saying that twice. Not saying that 10 times fast. So he was the engineer, he was the Russian scientist that developed the Soyuz rocket. Okay, I don't know if you remember, but Soyuz was the first satellite that was sent into space. Okay, so this is, let's see if we have here. So this was the first, the Sputnik. So sorry, not Soyuz. The Soyuz was the name of the rocket. He was the one that sent the Sputnik, okay, a satellite out into space. And so he developed this equation that basically governs how much fuel would you need in order to send something out of in space, depending on the velocity that you want to achieve. All right. And so in this article, in the International Space Station's article here of the rocket equation, it basically says, if you are going to go from the surface of the Earth to the orbit of the Earth, you need to achieve at least, okay, at least you need to achieve 8 kilometers per second. Okay. Do you remember when we were in the lesson when we were talking about Newton's cannon experiment? All right. And the idea is that in order to stay in orbit, you needed to go fast enough in order not to fall onto the Earth, but to keep falling, at the same speed that you were moving away from the Earth. Okay? And so, in order to stay in orbit, you need to at least achieve 8 kilometers per second. Once you are on Earth orbit, okay, once you are there, you are about moving at 8 kilometers per second. If you want to go from the orbit of the Earth, from Earth orbit to near Earth asteroids, you need to increase your speed by about 4 more kilometers per second. Okay, so that would allow you to get out of Earth orbit and onto the next place. Okay, if you want to go from Earth orbit to the surface of Mars or to Mars, you need to go 8 kilometers per second more, so 16 kilometers per second. So most of the times what you have is that rockets would have the first part of the rocket, the first stage of the rocket, okay, like this one here in the space shuttle that launches from the Earth, would have the huge, humongous, tanks and everything in order to put the rocket from the surface of the Earth to Earth orbit and to put it at 8 kilometers per second. Once you are there, then the probes would engage other engines in order to escape, okay, in order to escape the Earth trajectory and go on to the next part, the next phase. All right. So that is why you see in what was it in here in this article that we see that the that Dawn needed to go, okay, 15,449 kilometers per hour. Okay, so I don't know how much is that in kilometers per second. We can certainly figure that out, but that is the acceleration that it needed to achieve in order to go all the way, okay, to Vesta and then to Ceres, on its way actually out of Earth to go through Mars and then to the other asteroids. All right. So does that make sense? How you need to be able to accelerate that? Okay. So the first objective is to get into Earth orbit. That is the most expensive part of the whole trip. Okay. Because that is what takes the most energy to break away from the gravitational pull of the Earth. You are closest to the Earth, and that is, basically what is going to be holding you down. Okay? All right? And so here in the article, Petit discusses then the different types of propellants that you could have. All right? Solid rocket, kerosene, oxygen, and what is the type of propulsion that they give you. Okay? Hypergols, all right, or hypergolic propellants. Those are propellants that don't need an ignition system. And you also can study more on that. Methane oxygen gives you a propulsion of 4.5 kilometers per second. Okay, and so the one that has the most punch basically is hydrogen oxygen. So if you have liquid hydrogen and liquid oxygen and you ignite those together, those would put you in 8.3 kilometers per second. Okay. There are some people are trying to see if they can use nuclear reactors as the source of energy and hydrogen as the propellant. All right. So all these ones, kerosene oxygen, methane oxygen, hydrogen oxygen, those are usually the propellants that are used in the rocket boosters. Okay, the rockets once they launch at first. All right. They need to be, the problem with these propellants is that they need to be kept very cold, okay, because in order to have liquid oxygen, you have to cool it down, or to have liquid hydrogen or methane, you have to really cool it down, pretty much to near absolute zero. And that is why in the pictures, of your Saturn V rocket and so on, right before they are going to launch, you see that they are kind of smoking, they have kind of tubes and everything. That is actually to keep the oxygen and the hydrogen cool right before you ignite everything, okay? Yeah. You can definitely guess something is going to go wrong with anything nuclear. Not necessarily. Actually, nuclear energy has been usually very, very safe. Okay, if you think about the amount of nuclear reactors that we have around the world and everything, there have been very few problems with them. Okay. And even those that have had problems, it hasn't been too bad, really. Okay, so nuclear energy is really something that we probably need to investigate more and think more about how to use that better. All right. So Petit basically keeps using this equation, okay, the Tsiolkovsky rocket equation, to tell us, depending on the type of propellant that we need, what is the percent of propellant that we need for the rocket. Okay, so if you are using kerosene and oxygen, 94% of your rocket has to be at the beginning, when you are going to launch, it has to be propellant. So only 6% of the rocket can be something else. All right. If you are using methane oxygen, 90% of the rocket has to start being propellant. So if your rocket, let's say that your probe, what you are going to try to put out in orbit, weighs, let's say, 1 pound, okay, so really, really light, something very small and very light, you need 10 pounds of methane oxygen propellant in order to shoot it out. Okay, so that is basically the equation. So that is what this article tells us, that rockets are, if you wish, not very efficient compared with other type of transportation. All right, so a large ship, it's about 3% propellant, and then 97% is the cargo, is what you are actually transporting, not the propellant. In a rocket, 85% is propellant, and then only 15% is rocket, probe, and everything else. All right? So I would like you, as you study these two websites, especially this one here with the equation, it is very, very easy to follow. Don't freak out, okay? Just read it carefully. But basically here is saying, let's suppose that we want to achieve the required orbital velocity of 7,800 meters per second. So 8,000 meters per second is basically the same as this 8 kilometers per second. Okay, so 1 kilometer is 1,000 meters. So here is saying that orbital velocity is 7,800 meters per second, so about the same type. So you put that in the equation right here, okay? Then you divide that by 340 seconds, the gravitational pull of the Earth, and this is assuming that you are going to send 1 kilogram up, okay? It can be 1 pound or whatever, but the result is basically that in this rocket, we will need, the initial mass of the rocket needs to be 10.39 kilograms, okay? So if you are going to send 1 kilogram up into orbit, the initial rocket needs to be about this much, all right? So this is rocket science, okay? Yeah, this is rocket science. And so as a rule of thumb, basically this guy says that about 90% of the mass of the rocket has to be propellant. So if the Firefly, let's suppose that we are going to design something that is, not very big, okay, but about this size, okay, a cube that size, it could be, expanded with panels and so on afterwards. Everything would be folded in. And let's say that we estimate that this is going to weigh, I don't know, how much would it be if we have communication systems, cameras, a propulsion, an ion engine in it, and so on. Let's assume or propose that it's going to weigh, 10 kilograms. All right. So if it's going to be 10 kilograms, that is about 20 pounds. So to give you an idea, so what would be something close to weighing 20 pounds? So a bag of flour, sometimes it is, 25 pounds. Okay, so that is, a pretty heavy chunk. All right. So maybe less. I don't know. You decide how much, but when you have that decision made as a team, you estimate how much our probe is going to weigh, okay, then you can decide, okay, if we are going to do that, we will need this many pounds of propellant, okay, 90% more of propellant in order to send that at least to Earth orbit. And then you need to decide, how am I going to change it from Earth orbit to higher orbit to give it the extra propulsion that it needs in order to reach its destination. All right? So there's here another article about how rocket engines work, all right? And it explains about thrust, and the big external tanks, the solid rocket boosters, and so on. So that gives you all an idea of the many different types of propulsion that you would have. Here is an article on the hypergolic propellant, all right, or the hypergols. These are very interesting propellants because they do not need an ignition system, okay? So these are propellants that spontaneously ignite when they come in contact with each other, all right? So what happens is in the rockets, okay, when they do the countdown and everything, and they go, 5, 4, 3, 2, 1, ignition. Okay, ignition is basically the ignition system that mixes the kerosene and the oxygen or whatever, and then sends the ignition, okay, to actually start the explosion of the rocket. Okay, a rocket is really a huge control explosion, and so that ignition system sometimes is very difficult to manage, and so many times space probes use these hypergolic propellants. Once they are out in space, they use this in order to avoid having the ignition system. You don't need the ignition system. You just mix the two propellants together and they ignite by themselves. All right? So, for example, in the Apollo mission, do you remember, okay, when after they landed on the moon, after they did everything that they needed to do there on the moon, they were on the moon, and then they got into the lunar module, and they propelled the lunar module out from the moon in order to rendezvous again with the service module. Okay, well, that propellant that they use there for launching off the moon use hypergolic propellants. Okay, because they just needed to combine the two things, explode, and shoom, and go. Okay, they didn't need, the moon has a smaller gravitational pull, so they didn't need a large engine for that, but that was what they used. So they used this type of hypergolic propellant for that. Okay, all right.
How does it work?
Sorry?
How does it work?
How does it work? So, the great question. So here in the website, it basically explains that you have these propellants are basically a fuel and an oxidizer. And there's, here they have some of the examples of that. So dinitrogen tetroxide and hydrazine. So one is the fuel, this is the fuel, and this is the oxidizer. And then they are kept separate, okay? And basically all that they need in order to start the combustion is to just put them together, okay? So they would have tubes that they open, and then they put, one and the other together, and when they combine together, they ignite, they explode, all right? There are several things that do that also that don't need, anything else. So, for example, I remember in my brother's chemistry class, they were in the lab one time, and one of the students was making laughing gas. Okay, so it is a specific chemical, process to make laughing gas. And they thought that that was, very fun and everything. The problem is that pure laughing gas explodes in the presence of oxygen. Okay, and guess what do you have in a lab all around you, just in open air? All right, so they almost exploded the whole lab without knowing. All right, so there are several things, several combinations. Okay, so here you have the hypergolic combinations, different things that you could use to do this type of engine. Okay, so these are here you have a picture, hypergolic propellant tanks of the orbital maneuvering system of the space shuttle. All right, so let me see if we go here. So the space shuttle, it used some of these. You see the two different tanks, one for the fuel, okay, one for the fuel, another one for the propellant, and then the system would mix those two together. They would ignite and just do the thrust, okay, out here. All right, so this was one of the hypergolic engines using the space shuttle. Does that answer your question of how they would work? I don't. Okay. Okay, good. All right. So you could decide, for example, your probe, your Firefly probe could say, hey, sometimes we will need to change the trajectory of our probe. So we will have very small hypergolic engines. Okay, so I could have just, one part, of propellant, okay, and another fuel, an oxidizer, and then combine them together and send them on a thruster to generate enough thrust to change the trajectory of the probe. Does that make sense? Okay, so those are the type of engineering decisions that you also need to make in your project. All right, these are huge here because these were used for the space shuttle system, but they don't have to be big. Okay, you can miniaturize a lot of things. All right, and so sometimes you could also use these technologies, okay, in a smaller environments, but achieve the same results. All right. Okay. I spoke a lot today. So, any questions, guys? So you say there that it sounds like an airplane engine. Yeah. So what do airplane engines use? What do airplane engines use?
So what are we supposed to be doing with our group?
Okay, so the first part of the project is what? What is the first part of the project? What do you mean? I don't know. I don't know. Well, come on, Nathan. You have it there in the module written down. What is the first part of the project?
We're supposed to find something?
Yes. Define what?
I don't know.
What do you need to define? Let's see, brainstorm and figure out what we want to see in space. That's right.
Oh,
yeah. Okay, so define the purpose of the mission. All right. Yeah, what do you want to bring back? If you want to bring back something, all right, that is a lot more complicated because then you have to actually think about bringing something back, So, like in this case, all right, in the case of the case here of Deep Space One, all right, so the mission was to try out these new technologies and then rendezvous with a comet. Okay, so the mission was not to come back, so the probe didn't come back, but the mission was to do a rendezvous with the comet Borrelly. All right, so it had to intercept that. Haley says, and so we have to define the purpose of the mission and what system we would need to send it, gather it, and bring it back. So if you are going to gather something and bring it back, that is a whole lot more complicated. All right. So remember, in the website there of Deep Space Industries, let me see. Okay, if we go here to the website, all right. So we have that the Firefly was just prospecting. Okay, so this was just to go and gather information, just go and find out the information. Then you would have the Dragonfly that was for harvesting. That is actually a completely different mission, if you wish, because it's a lot more difficult. Now you are talking about landing, extracting material, processing it, and everything. And then if you are going to bring it, doing the processing, that is another issue, okay? And then the manufacturing things, if you are going to manufacture fuels or things in space. So imagine if you are going to be able to land a probe on an asteroid and be able to start manufacturing hypergolic fuel there in space, and then send it to other probes and everything. That would be very, very good. Okay.
Okay.
So this mission, I'm not asking you to actually try to bring something back. All right. I'm just saying, how about if you decide of doing something along the lines of prospecting? All right, just going, taking pictures of an asteroid, calculating what is the asteroid composed of, all right? Or you could decide to go to the sun, all right, only once. That would be a one-way trip. But it has been done, okay, going to the sun. You could decide, okay, let's go and do it again. Let's see, can we put something in orbit around the sun, close to the sun? Okay, or just go into the sun, So, but in this case, I'm actually thinking more about the idea of visiting maybe some asteroids, all right, for the purpose of knowing what is the asteroid made of, okay, and then later on you would think about sending a probe to harvest something. So you just want us to create our own Firefly, to take pictures and things, and you want us to land somewhere, right? Okay, landing is up to you. If you want to land it, that's fine. Yeah. So yeah, this is not lava. The sun is not lava. The sun is superheated plasma. All right. So yeah, it's not a really hot gas. It is really a hot gas that turns into plasma. Okay.
Mr. Roboli, did
Yes.
you record this class?
Yes, I did, and I'm doing it.
Oh, because it doesn't say down here that it's being recorded.
Oh, no problem. Don't worry. So I'm recording it in another software here, not with the GoToMeeting.
Okay.
Yeah. So Rodrigo, if you want to go to Pluto, that's fine. You can also do that. Voyager, they have gone out of the solar system. It just takes several years. All right. So it's just a matter of patience and planning. Okay. And then you can decide how are you going to get there. Okay. It's proven that you can practically live on the moon Titan. I don't think that has been proven at all, Mac. What are you talking about? Okay. Now that would be a mission, to send something to Titan, all right, and see if there is an atmosphere, if it's something that it could be explored that way. Okay. So those are the things that you can decide. Okay. Sounds good, Nathan. Now that you are paused, that does answer your question.
Yeah, it does.
Right. Okay, so I don't want anyone to say, so what are we supposed to do? I don't know. Okay, come on, guys. All right. Okay. Do you have any other questions? Okay. Or are you? I call building a moon base. That would be cool. That would be actually amazing. So that would take a lot of transporting things. Okay, so that is part of that is the big problem really that we have now is how to put things in orbit. Okay, how to put large amounts of stuff in orbit. It takes so much, like we were seeing, here in this website. Okay, the energy cost of going from the surface of the Earth to Earth orbit to gain those 8 kilometers per second, that is the most costly part of the trip. And so if you are going to build a moon a base on the moon, the problem that we have is really how are we going to send all that stuff up? That is one of the reasons why here in Deep Space Industries, they are thinking, could we use and manufacture things in space and then send them from an asteroid, basically harvesting things in the asteroid, manufacturing something, and then send it to the moon there. Because that would actually be maybe cheaper than trying the other way around, as far as propellant goes. Okay, that is the main thing. All right. So Jens wants space lemonade. Okay, I don't know. Now we are in the silly time. Okay, guys, let's call it a day. All right. And let's see, who would like to offer a prayer for us? Mac, do you have a mic around?
Yeah, I got it.
Okay. Would you like to pray for us?
Sure.
Thank you.
All right. Dear Heavenly Father, we're thankful for this day. We're thankful for the many blessings you've given us, and we're thankful for Mr. Aboldi being able to teach us today. And please bless that we may have the Spirit to be with us, and that we may be happy and good. We see these things in the name of Jesus Christ. Amen.
Amen. All right. Well, thank you very much. And we'll see you next time.